So in this session, we will continue with chapter number 10, cluster analysis, basic concepts and methods. So in face-to-face class, we discussed basic concepts of cluster analysis, and we begin with partitioning methods. So in this session, we will continue with hierarchical methods, density-based methods, grid-based methods, evaluation of clustering, and summary. So before starting this session, I will ask you some questions to review all the topics covered in face-to-face class. So what's the meaning of cluster analysis? Can you give me another terms equivalent to cluster analysis? Yes, it is unsupervised learning, okay? But we can say cluster analysis or other terms. We can say clustering, we can say data segmentation. Is to find similarities between data according to the characteristics found in the data and grouping similar data objects into clusters. Okay. What's the meaning of a good clustering? Good clustering. Yes, good clustering, that means so good clustering means high intra-class similarities and low inter-class similarity. Yes. So good clustering method will produce high quality clusters with high intra-class similarity and low inter-class similarity. Okay, let's move now to partitioning approach. So there are many examples or techniques of partitioning methods like k-means and k-midwidths. So what is the difference between k-means and k-midwidths? The difference between k-means and k-midwidths. So the difference between k-means and k-midwidths, yes. So in k-means we calculate the center. Yes. But in k-midwidths, the center must be one of the tuples. Yes. Yes, the nearest, we will consider the nearest object as a center. Very good. So, can you give me one disadvantage of k-means? Disadvantage of k-means. So one of the disadvantages of k-means, the user has to fix the number of groups. So the user has to fix the number of groups. We cannot make clustering without specifying the number of groups. So k is the number of groups. We have to specify number of groups. Okay. Let's move now to hierarchical methods. So for hierarchical methods, there is a hierarchy. We will use distance matrix as clustering criteria, and this method does not require the number of clusters k as in input. So the advantage of hierarchical clustering is this method does not require the number of clusters, but needs a termination condition. So this is an illustration of two methods of hierarchical clustering. The first one is agglomerative. Agglomerative, that means in the first step here, in the first step, we have each tuple is, so each tuple, each object represents a group. So in step number 1, we will merge together two objects. Okay, in our example, we merge A and B. So the nearest objects will be merged together to form one group. In the step number 2, we will merge two other objects. So if we begin with each object represents one group, and in every step we will merge objects together to represent a group. In this case, we talk about agglomerative function, agglomerative method. This is the first method. The second method, so here the reverse method is divisive. We will begin with all the data together in group, and we will divide this data to create subgroups. So in each iteration, we divide one group to two groups. It is clear? Any questions about hierarchical clustering? Yes. Indiana is reverse to agglomerative, to Egan's. Let's begin with the agglomerative nesting. So it is implemented in statistical package and use the single link. We will discuss together what's the meaning of single link in the next slides. It uses the single link method and the dissimilarity matrix. The idea is to merge nodes that have the least dissimilarity, and eventually all nodes belongs to the same cluster. So here dendrogram, so shows how clusters are merged. Decompose data objects into several levels of nested partitioning, tree of clusters. So the tree of clusters is called a dendrogram. A clustering of the data objects is obtained by cutting the dendrogram at the desired level, then each connected forms a cluster. Each connected compound forms a cluster. So let's see together how we can create a dendrogram. Let's suppose that this is my data. E, C, D, E, F. So let's suppose that the distance between E and D equal 1. Let's suppose that this distance equal 1, this distance equal 1.5. So how we can calculate the dendrogram? In the first step, we have to merge the two nearest tuples. What are the two nearest tuples in this example? Yes, E and D. So we will merge E and D together with a value of 1 as distance. After that, the two nearest neighbors are E and C. So E and C will be merged in distance 1.5. After that, so this is after that, this one. After that, we will merge F with A and C or with D and E. After that, F will be merged with A and C. Yes. So we will merge F with A and C. Here F. Let's suppose that the distance is X. After that, we will merge all the groups together. We will merge all the groups together. We will obtain our dendrogram. It is clear? It is clear how we can, how we can create our dendrogram from hierarchical clustering. After that, we have to cut this dendrogram. For example, if I cut this dendrogram here, this is the first intersection, this is the second intersection. So the clusters will be, this is the first cluster, group number 1, and this is the second cluster, group number 2. It is clear how we can extract groups from dendrogram? Okay. Let's suppose, for example, I will cut this dendrogram here. I will obtain how many clusters? 3. Very good. This is the first one. This is the second one, and this is the third one. 3 clusters in this case. This one, and this one. 3 clusters if I will cut my dendrogram in this level. So here we discuss, or we merge 2 groups of data. Okay, so we say we can calculate the distance between 2 tuples, but we don't have an idea about how we can calculate the distance between 2 groups of data. So Diana is the reverse. So distance between clusters, how we can calculate distance between clusters, how we can evaluate this distance. This is the question. So there are many manners to calculate the distance between clusters. The first one is a single link. Yes, by Euclidean distance it's okay, but here we have many tuples in the green group and many tuples in the blue group. So how we can evaluate this Euclidean distance? We will suppose that this is the distance, the red one, or the blue one, or the green one. So there are many manners to evaluate the distance between clusters. Let's begin with the first manner, single link. So single link, that means we will consider the smallest distance between an element in one cluster and an element in the other. So for single link, we will calculate all the possible distances between all the tuples from the cluster number 1 and cluster number 2. After that, we will consider the smallest distance. Single link, that means smallest distance. It is clear? After that, complete link. So complete link, that means we will consider the largest distance, largest distance between an element in one cluster and an element in the other. After that, other possibility, the average. We can also calculate the average. Is the average of all distance between an element in one cluster and an element in the other. The centroid. Centroid is the distance between the center of two clusters. Like your proposition, Mr. Walid. We can calculate, Mr. Walid and Mr. Faisal. We can calculate the distance between the center of cluster number 1 and cluster number 2. Midword. We can calculate the distance between the midwords of the two clusters, not the center, but the midwords. So there are many manners to calculate the distance between clusters. It is clear? Let's see together how we can calculate the middle of a cluster. So the middle of the cluster, the centroid is the middle of the cluster. That means we will make an average of all the tuples. The radius, so this is the centroid. The radius of a cluster is the square root of average distance from any point of the cluster to its centroid. So we will calculate the distance between all the tuples and the center of this cluster. After that, we perform the square root of the average. The diameter is the square root of average mean squared distance between all pair of points in the cluster. So for a cluster, we can calculate the centroid, the radius, and the diameter. Any questions? Extensions to hierarchical clustering. So okay, without examples, just theory. Okay. Measure weakness of agglomerative clustering methods. So the problem with hierarchical clustering can never undo what was done previously. and do not scale well. So the time of complexity is O(n power 2), when n is the number of total objects. Integration of hierarchical and distance-based clustering, we can find Birch. This is the first technique. So this technique uses CFIT tree and incrementally adjust the quality of subclusters. The second technique is chameleon, is an hierarchical clustering using dynamic modeling. So this is the description of the first method, and this is the description of the second method. Let's move now to density-based methods. So density-based clustering methods, clustering based on density, such as density connected points. The major features of density-based clustering methods are: discover clusters of arbitrary shape, handle noise, one scan, meet density parameters as termination condition. And there are several interesting studies in density-based clustering method, like dbScan, optics, donclude, and click. Any questions? For density-based clustering, there are some concepts. For example, EPS is the maximum radius of the neighborhood, and mean points is the minimum number of points in an EPS neighborhood of that point. So we can define an EPS of Q as P belongs to D with distance between P and Q is less than EPS. Another concept, the concept of directly density reachable. So a point P is directly density reachable from a point Q with respect to EPS and mean PTS if P belongs to an EPS of Q and core point condition. So n EPS of Q is more than mean PTS. Any questions? Are you here? So this is an example. P, this point P, is directly density reachable from Q. This is Q, this is P. Why? Because P belongs to n EPS of Q. That means the distance between P and Q, this distance, is less than 1 centimeter, less or equal. In our example, is equal. And the second condition, the number n EPS of Q is more than mean points. So n EPS of Q here, how many points that belongs to D, and the distance between P and Q is less than EPS. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here 10 is more than 5. So there are two conditions to verify, And if these conditions are verified, we can say that this point is directly density reachable from another point. Here we discuss together directly density reachable, directly. P and Q directly density reachable. We can also see together density reachable without directly density reachable. So in our example here, we have P1, so we have Q, P1, and P, 3 points. This one, and this one. Here we can say that a point P is density reachable from a point Q, density reachable from a point Q with respect to EPS and mean points if there is a chain of points P1, P2, Pn with P1 equal Q, Pn equal P, such that Pi plus 1 is directly density reachable from Pi. So in our example, P is directly reachable from P1, and P1 is directly reachable from Q. So we can say that P is density reachable from Q. It is clear? The third concept is density connected. So a point P is density connected to a point Q. This is an example of density connected. Here we have P and here we have Q with respect to EPS and mean points. If there is a point O such that both P and Q are density reachable from O. So here in our example, P and Q are density reachable from O. For this reason, we can say that P is density connected to a point Q. It is clear?
Yes, clear.
Good. So dbScan is an example of density-based method. The dbScan is the abbreviation of density-based special clustering of application with noise. So this method relies on a density-based notion of cluster, and a cluster is defined as a maximal set of density-connected points. This method discovers clusters of arbitrary shape in special databases with noise. This is an example. We can find a demo of dbScan in the link. Optics also can be considered as a density-based method. So optics is the abbreviation of ordering points to identify the clustering structure. This method produces a special order of the database with respect to its density-based clustering structure, and this clustering ordering contains information equivalent to the density-based clusterings corresponding to a broad range of parameter settings, good for both automatic and interactive cluster analysis, including finding and tracing clustering structure. And this method can be represented graphically or using visualization techniques. Now we will move to grid-based methods. We discussed together partitioning methods, hierarchical methods, density-based methods, and now grid-based methods. So grid-based methods using multi-resolution grid data structure. This is the specificity of this method, multi-resolution grid data structure. There are many methods that can be considered as grid-based method. STING is a method, the abbreviation of Statistical Information Grid Approach. CLIC, so CLIC can be considered as grid-based and subspace clustering. Your attention please. CLIC can be considered as grid-based and subspace clustering. Wave cluster is a multi-resolution clustering approach using wavelet method. This is an illustration of STING, Statistical Information Grid Approach. So the spatial area is divided into rectangular cells, and there are several levels of cells corresponding to different levels of resolution. So here, for example, we have first layer. Here we have the second one, etc. So there are many levels. The STING clustering method, so each cell at a high level is partitioned into a number of smaller cells in the next lower level. Statistical info of each cell is calculated and stored beforehand and is used to answer queries. Parameters of higher level cells can be easily calculated from parameters of lower level cells. Here, for example, if we have parameters of this layer, we can calculate the parameters of this layer. So the STING clustering method uses a top-down approach to answer spatial data queries and starts from a pre-selected layer, typically with a small number of cells. And for each cell, the current level computes the confidence interval. Yes, there is a similarity. STING algorithm and its analysis. So remove the irrelevant cells from further consideration. When finished examining the current layer and proceed to the next lower level. Repeat this process until the bottom layer is reached. The advantages of STING algorithm: query independent, easy to parallelize, incremental update, and the complexity is out of key, with k is the number of grid cells at the lowest level. The disadvantages of STING algorithm: all the cluster boundaries are either horizontal or vertical, and no diagonal boundary is detected. Here we can find the description of CLIC. So CLIC can be considered as both density-based and grid-based. It partitions each dimension into the same number of equal length interval, and it partitions an m-dimensional data space into non-overlapping rectangular units. A unit is dense if the fraction of total data points contained in the unit exceeds the input model parameter, and a cluster is a maximal set of connected dense units with a subspace. We can find here in this slide the major steps of Click. The first one is the partition of the data space and find the number of points that lie inside each cell of the partition. The second one is to identify the subspaces that contain clusters using the a priori principle. Identify clusters, that means determine dense units in all subspaces of interest, and determine connected dense units in all subspaces of interest. Generate minimal description of the clusters, so determine maximal regions that cover a cluster of connected dense units for each cluster. Determination of minimal cover for each cluster. So, strength and weakness of Click. Click is insensitive to the order of records in input and does not presume some canonical data distribution. Also, scales linearly with the size of input and has good scalability as the number of dimensions in the data increases. The problem of Click is the accuracy of the clustering result, so this accuracy may be degraded at the expense of simplicity of the method. Let's move now to evaluation of clustering, how we can evaluate clustering. There are many manners to determine the number of clusters. The simple manner is empirical method. So the number of clusters, K, equal square root of n divided by 2 for a data set of n points. For example, if n equal 200, K equal square root of 200 divided by 2, K equal 10. Ilboy method, so use the turning point in the curve of sum of within cluster variance with respect to the number of clusters. We can also use cross-validation method. We will divide a given data set into m parts. We will use m-1 parts to obtain a clustering model, and we use the remaining part to test the quality of the clustering. After that, for each point in the test set, find the closest centroid and use the sum of squared distance between all points in the test set and the closed centroids to measure how well the model fits the test set. For any k more than 0, repeat it m times, compare the overall quality measure with respect to different k's, and find number of clusters that fits the data the best. This is, on this slide we discussed together 3 manners to determine the number of clusters. Any questions? Now we will discuss together how we can measure the clustering quality. There are 3 kinds of measures: external, internal, and relative. For external, supervised, employ criteria not inherent to the data set. We will compare a clustering against prior or expert specified knowledge using certain clustering quality measure. For internal and supervised, so the criteria derived from data itself, we will evaluate the goodness of a clustering by considering how well the clusters are separated and how compact the clusters are. The third measure is relative. Directly compare different clusterings, usually those obtained via different parameter settings for the same algorithm. Any questions about these measures? Can you see the difference between external, internal, and relative? So in this slide, we discussed together some commonly used external measures. The first one is matching-based measures. We can find purity, maximum matching, F measure. The entropy-based measures, conditional entropy, normalized mutual information, variation of information. Pairwise measures, there are 4 possibilities: the true false, the true positive, the false negative, the false positive, and the true negative. Jaccard coefficient, correlation measures, etc. So there are many external measures that can be used to evaluate the clustering. Summary. So cluster analyzes groups objects based on their similarity and has wide applications. Here we discuss what's the meaning of cluster analysis, how we can obtain a good clustering. After that, we said that measure of similarity can be computed for various type of data. So for example, if we have numeric data, in this case we can use Euclidean distance. If we have not numeric data but binary data, we can use Jaccard index, etc. Clustering algorithms can be categorized into partitioning methods, hierarchical methods, density-based methods, grid-based methods, and model-based methods. For example, for partitioning methods, we can code k-means and k-midwidths. So k-means and k-midwidths algorithms are popular partitioning-based clustering algorithms. Burge and Chameleon are interesting hierarchical clustering algorithms, and there are also probabilistic hierarchical clustering algorithms. So for hierarchical algorithms, we said that we have to create a dendrogram, and after that we will cut this dendrogram to extract groups. DB-scan, optics, and DunClue are interesting density-based algorithms. Sting and click are grid-based methods where click is also a subspace clustering algorithm. The quality of clustering results can be evaluated in various ways. We can use external manner, internal, or relative. Any questions about this? Yes? In relative, we will compare different clustering. That means I will use this algorithm, another algorithm to obtain many manners of clustering. We can also, for example, if I use k-means, I can use different value of k. So different parameter settings for the same algorithm. After that, I will compare the result from the setting number 1, setting number 2, setting number 3, and after that I will decide what is the best, or what is the what clustering has a high quality. Relative here because we will compare different clustering. It is clear? So after that, when we compare, we can use supervised or unsupervised. After that, when we compare, we have to compare the performance. We can use external or internal manner. Yes. But here, we have to, for the same algorithm, we have to make different parameter settings. After that, okay, after that we have to select the best one, the best clustering. Other questions?
Thank you, Dr. Rضوان.
Okay. You are welcome. See you next week, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.